economics, business, insurance, mathematics, auto racing, and the list goes on, are fields in which the analysts use mathematical modeling to maximize profits or production or minimize costs. Hi, my name is Jason Rosenberry, and that's what we will be doing in today's lesson. Applying the first derivative to solve maximum and minimum problems in real-world applications. Let's look at the strategy for solving these types of problems. Strategy for solving max-min problems. 1. Understand the problem. Read the problem carefully. Identify the information you need to solve the problem. 2. Develop a mathematical model for the problem. Draw pictures and label the parts that are important to the problem. Introduce a variable to represent the quantity to be maximized or minimized. Using that variable, write a function whose extreme value gives the information sought. 3. Graph the function. Find the domain of the function. Determine what values of the variable make sense in the problem. 4. Identify the critical points and endpoints. Find where the derivative is 0 or fails to exist. 5. Solve the mathematical model. If unsure of the result, support or confirm your solution with another method. 6. Interpret the solution. Translate your mathematical result into the problem setting and decide whether the result makes sense. Let's look at a mathematics example. Minimizing perimeter. What is the smallest perimeter possible for a rectangle whose area is 16 square inches, and what are its dimensions? Let's first draw a rectangle to model the situation. So here's a rectangle, and we know the dimensions of a rectangle. We usually label L for length and W for width, and we're told that the area of this rectangle must be 16 square inches. So what do we know? We know that area is equal to length times width, so 16 must equal length times width. We're trying to minimize perimeter. Perimeter is found, P, perimeter, 2 times the length plus 2 times the width. This is the equation that we wish to minimize. We want to minimize P. So let's try to get P in terms of one variable, either L or W. So we're going to solve our area equation. 16 equals L times W. Let's solve that for L. L is equal to 16 divided by W. We will now substitute that expression for L into the perimeter equation. So now perimeter P is equal to 2 times L. L is 16 over W plus 2 times W. So now we have a function in terms of W that gives us perimeter. Let's clean this up. We have perimeter P is equal to 32 over W plus 2W. Now let's find the derivative of P. P prime would equal the derivative of 32 over W would be negative 32 over W squared plus the derivative of 2W, which is just 2. Now we want to set the derivative equal to 0 and solve. So 0 equals negative 32 over W squared plus 2. Multiplying both sides of the equation by W squared gives us 0 equals negative 32 plus 2W squared. Continuing to solve for W, we get 2W squared equals 32, which implies that W squared is equal to 16. Taking square root of both sides, W would equal plus or minus the square root of 16, plus or minus 4, but the width of a rectangle cannot be negative, so we throw out the negative 4. So we have W is equal to 4. Now we can solve our problem. Letting W be 4, substituting W equals 4 into the length equation, length would equal 16 over 4, So our length is also equal to 4. So our rectangle is actually a square. Notice 4 times 4 gives us the area required, 16 square inches. So to answer the question, the dimensions of the rectangle would be 4 inches by 4 inches, and the perimeter of this rectangle would be 16. Let's try another. Finding an angle. Two sides of a triangle have length A and B, and the angle between them is theta. What value of theta will maximize the triangle's area? And here's a hint. Area of a triangle can be found by 1/2 times A times B times sine theta. So here we have the given area equation, A equals 1/2 AB sine theta. And using implicit differentiation, we will differentiate both sides of this equation with respect to theta. So let's go ahead and, on the left-hand side, we would have d theta of A is just dA over d theta. And over on the right-hand side, when we differentiate this with respect to theta, 1/2 AB is treated as a constant. So we would simply get 1/2 AB times derivative of sine theta with respect to theta is cosine theta. So here we have our first derivative, and now let's set this derivative equal to 0. So we have 0 equals 1/2 times A times B times cosine theta. So the only way for this to be a true statement is if for A to be 0, which is impossible. A represents the length of a side. Also B cannot equal 0. It must also be the length of a side. So this forces cosine theta to equal 0. So in solving the equation cosine theta equals 0, there are actually an infinite number of solutions to this equation. However, since we're working with a triangle, we have to make sure that the angles add up to give us 180. Therefore, that eliminates all the solutions but one. So theta must equal pi over 2, which is equal to 90 degrees. Let's carry these ideas to an example from business or industry. Designing a poster. You are designing a rectangular poster to contain 50 square inches of printing with a 4-inch margin at the top and bottom, and a 2-inch margin at each side. What overall dimensions will minimize the amount of paper used? So here's a picture that represents our situation. The outer rectangle, larger rectangle, represents the size of the poster, and the inner rectangle represents the area of print. We're told that the area of print must be 50 square inches. So the area of the inner rectangle would be 50 square inches. We're also told that the top and bottom of our poster has a 4-inch margin. So this distance and also this distance would be 4 inches. 4 inches, and the left-right margins are 2 inches. So we have 2-inch margin and a 2-inch margin. Now let's let L and W represent the length and the width of the print area. So distance from here to here we're going to call L, or W, doesn't matter which one. Let's call it W. And the distance from here to here we're going to call L. So here's L and here's W. And I know that L times W is 50. L times W equals 50. Now let's talk about the area of the large rectangle, the area of the poster. Area of the poster can be found by taking W, which again, remember W is the distance from here to here. So what would the whole thing be? Well, here's 4 inches plus 4 inches is 8 inches plus W. So W plus 8 would represent this entire distance. Likewise, for the length of the poster, 2 plus 2 is 4. 4, we're going to add that onto L. So L plus 4 would represent the poster's length. Now we have an area function that we want to minimize. So first we need to write that in terms of one variable. So let's go ahead and solve this equation for W. So W would equal 50 over L. We'll now substitute that value in for W here. So the area function that we need to minimize, A, would equal the quantity 50 over L plus 8 times L plus 4. So, multiplying our area equation out, multiplying the quantities together, we get A equals 50 plus 200 over L plus 8L plus 32. Combining like terms, we get A is equal to 200 over L plus 8L plus 32 plus 50, 82. Again, here's the function we want to minimize. So let's find the derivative. What would A prime be? The derivative of 200 over L would be negative 200 over L squared. Derivative of 8L is plus 8, and the derivative of the constant is 0. So A prime equals negative 200 over L squared plus 8. We will now set that derivative equal to 0 and solve. So we set the derivative equal to 0. Let's now multiply everything by L squared, giving us 0 equals negative 200 plus 8L squared. This implies that 8L squared would equal 200. L squared is equal to 25. L is equal to plus or minus 5, but we need to throw the negative 5 out because the length of a poster cannot be negative. So we get an L value of 5. Length is 5. Now again, remember what L represents. L is the length of the print area. So let's first find the length and width of the print area. If L is equal to 5, then our width, W, would equal 10 inches. Now that's not the overall dimensions of our poster. Remember that because of the margins, let's figure out the width of the poster first. So W being 10, we need to add on 8 more inches for the margins. So that's a distance of 18 inches, and the length of our poster would be the L value 5 plus 4 inches of margin. 5 and 4 make 9 inches. So the overall dimensions of our poster would be a 9-inch by an 18-inch poster. Let's try an example from economics. Suppose R of x equals 9x represents revenue, and C of x equals x cubed minus 6x squared plus 15x represents cost, with x measured in thousands of units. Is there a production level that maximizes profit? If so, what is it? Maximum profit occurs when marginal revenue equals marginal cost. Remember that marginal means first derivative. So let's find marginal revenue. R prime of x, or the derivative of the revenue function, would just be 9. And the marginal cost function would be derivative of cost, which would be 3x squared minus 12x plus 15. And again, maximum profit will occur where those two are equal. So let's set R prime of x equal to C prime of x. So that yields 3x squared minus 12x plus 15 equals 9. And now we'll solve this equation for x. So we get 3x squared minus 12x plus 6 equals 0. Go ahead and factor out a factor of 3. So that gives us 3 times the quantity x squared minus 4x plus 2. And that equals 0. So let's solve this equation for x using the quadratic formula, which means we only need to worry about this factor. So again, using quadratic formula, our a value would be 1, b would be negative 4, and c would be positive 2. So using quadratic formula, x would equal negative b, negative negative 4 is positive 4, plus or minus the square root of b squared, negative 4 squared is positive 16, minus 4 times a, which is 1, times c, which is positive 2, all over 2 times a, 2 times 1 is 2. This gives us x equals 4 plus or minus the square root of 16 minus 8, which is 8, all of that over 2. The square root of 8 can be simplified to 2 root 2, that's all over 2, and now we can divide out a common factor of 2, giving us 2 plus or minus the square root of 2. So we have two solutions here, 2 plus the square root of 2 and 2 minus the square root of 2. 2 minus the square root of 2 is approximately equal to 0.586, and 2 plus the square root of 2 is approximately equal to 3.414. So here we have our two critical values, 2 plus the square root of 2 and 2 minus the square root of 2. And now we want to try to determine which one maximizes profit. And there's two ways to go about this. We could actually take these values and plug them into the profit function, evaluate the profit function using those values to see which one gives the larger amount. So that'd be a numerical technique or a numerical method for solving that problem. Or we could look at the graph, and here on the left hand side we have the revenue function 9x, red line being the graph of the revenue function, and the blue curve being the graph of the cost function x cubed minus 6x squared plus 15x. So now let's take a look at what's going on with these two graphs at these two values. And look here at 2 plus the square root of 2. Here we can see that at x equals 2 plus the square root of 2, here we can see the revenue function value, the money coming in, is much larger than the cost function value, money going out. So in that case, you would have a profit. So 2 plus root 2 maximizes profit. Versus 2 minus the square root of 2, here at this x value, we can clearly see that cost is larger or greater than revenue. So there would be a loss. So the value of x that maximizes profit would be 2 plus the square root of 2. Now it's time for you to try a problem. Suppose r of x equals 8 root x represents revenue, and c of x equals 2x squared represents cost, with x measured in thousands of units. Is there a production level that maximizes profit? If so, what is it? Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So here we have our revenue and cost functions, and to find maximum profit again, we want to set marginal revenue equal to marginal cost. So marginal revenue, or r prime of x, would equal the derivative of 8 root x. So again, we think of that as 8x to the 1/2. So this would be 4 times x to the negative 1/2. And the marginal cost function, c prime of x, would equal 4x. We want to set these two equal to one another. So let's set 4x to the negative 1/2 equal to 4x. So dividing both sides by 4, this would imply that x to the negative 1/2 equals x. And the only value of x that would make this a true statement is x equals 1. Recall that x is measured in thousands of units, so your answer would be 1,000 units. In this lesson, we applied the first and second derivatives to maximum and minimum problems from many real-world examples. Be sure to work the exercises that your teacher assigns, and we'll see you next time.